Bitcoin. I'm sure you've seen the headlines, the crazy price swings, all the hype. But underneath all that noise is a really revolutionary piece of technology. So today, we're going to ignore all the speculation and go straight to the source. We're going to break down the original blueprint to see how it actually works, and then we'll look ahead at a future threat that could challenge its very existence. Let's dive in. It all started right here, with this one sentence from that 2008 white paper by the anonymous, mysterious Satoshi Nakamoto. And the goal, it was simple, but honestly pretty revolutionary. Create digital money that works just like physical cash. I mean, think about it. You can hand a dollar bill to someone without asking a bank for permission, right? So why couldn't we do that online? This was the exact problem Bitcoin was built to solve. So, to really get the solution, we have to understand the problem first. And the problem, as Satoshi saw it, was trust. Or more specifically, our total reliance on these trusted third parties, banks, to handle every single electronic payment we make. And this slide really breaks down the hidden costs of all that trust, because banks have to mediate everything. Transactions can be reversed, which creates a lot of uncertainty. They tack on fees that make tiny payments, micropayments, basically impossible. And to protect themselves, merchants have to collect way more of our personal data than they should ever need to, all while everyone just kind of accepts that, a certain amount of fraud is just part of the deal. This was Satoshi's really radical idea. What if instead of trusting an institution, we could just trust math? What if we could build a system where transactions are verified not by some middleman, but by cryptographic proof that absolutely anyone can check for themselves? This is the huge shift in thinking that makes Bitcoin possible. Okay, so how do you actually build something like this? Well, the very first step is to define what a digital coin even is. And the answer is surprisingly elegant. See, a Bitcoin isn't a file on your computer that you can just copy and paste. The white paper defines it way more simply. It's a chain of digital signatures. Think of it less like a digital file and more like a physical check that gets endorsed by each new owner. The coin's entire history, its whole life story, is written right on the coin itself.
So the process is pretty cool. To send a coin, you digitally sign it over to the next person. You use their public key, which is kind of like a bank account number you can share with anyone, and you sign the whole thing with your private key, which is like your secret PIN that proves you're the real owner. This new signature gets added to the coin's history, and now the new owner can check that whole chain to prove it's theirs. Simple, right? Well, almost.
And boom, we've just hit the central problem of all digital cash, double spending. If I have a digital coin, what's stopping me from sending that exact same coin to you and also to someone else? With a file, it's easy, you just copy and paste. But with money, that would be total chaos. The system needs a foolproof way to agree on which transaction happened first. Satoshi's solution was genius. Instead of having a central bank keep a private ledger hidden away somewhere, what if we just announced all the transactions to everyone, and then had a system for the whole network to agree on the exact order they happened in? This shared history? Well, that's the blockchain. This slide does a great job of showing how differently Bitcoin thinks about money. A bank uses an account model. You have a balance, and transactions just change that number up or down. But Bitcoin uses something called the UTXO model. Your balance is really a collection of individual chunks of digital cash, unspent outputs from old transactions. So when you spend, you're not just editing a number. You're actually consuming old UTXOs and creating new ones, kind of like handing over physical bills and getting change back. Okay, so a public ledger of every transaction ever. That sounds like a ton of data, right? To keep things from getting out of hand, Bitcoin uses this really clever trick called a Merkle tree. It takes all the transactions in a block and gives each one a unique digital fingerprint, called a hash. Then it pairs them up, hashes the pair, and just keeps doing that all the way up the tree until you're left with one single fingerprint at the top, the Merkle root. That one tiny piece of data represents every single transaction in the block. It's super, super efficient. So we've got our coins, we've got our public ledger, and a slick way to manage all the data. But what makes it all secure? What stops someone from just rewriting history to their own advantage? This is where we get to the absolute engine of the whole system, proof of work. Proof of work is the magic ingredient that makes sure everyone agrees on the single true history of transactions. To add a new block of transactions to the chain, network participants, who we call miners, have to solve this incredibly difficult, but easily verifiable, computational puzzle. It's like a global race to find a winning lottery ticket. and it requires real-world resources, computer power, and a whole lot of electricity. And this is what builds the fortress. Proof of work basically creates a one CPU, one vote system. The longest chain of blocks is the official one because it represents the most computational work. So to change a transaction from the past, an attacker would have to secretly resolve the puzzle for that block and for every single block that came after it, all while trying to outcompute the entire rest of the global network combined. It's a race against time and energy that they are mathematically guaranteed to lose. So, here we have this incredibly elegant self-securing system built on cryptographic proof, and for more than a decade, it's worked. But what happens when a new kind of computer comes along? A computer that's specifically designed to break the very math that holds this whole thing together. We're talking, of course, about quantum computing.
Look, Bitcoin security isn't magic. It's really just based on the fact that certain mathematical problems are incredibly difficult to solve. At least, they're incredibly difficult for the classical computers we have today. But quantum computers? They're a whole different beast.
Let's get specific. Bitcoin's security, as you can see here, is built on two main pillars. First is the ECDSA algorithm. That's what creates the digital signatures that prove you own your coins. Think of it as a mathematical lock that's pretty much impossible to pick. Second is the SHA-256 hash function. That's the engine of proof of work. It's a one-way street, easy to do but impossible to reverse. These two tools are fortresses against today's computers.
And this slide lays out the threat perfectly. You see, there are specific quantum algorithms that are literally tailor-made to break these exact tools. Shor's algorithm is designed to crack public key cryptography like ECDSA, which could let an attacker forge signatures and just steal money. And Grover's algorithm gives a massive speed up on search problems, which could seriously undermine the SHA-256 hashing at the very heart of mining.
Now, this isn't just theory. Researchers have actually done the math on this. To crack a Bitcoin signature in that 10-minute window before a transaction is confirmed, you'd need a quantum computer with an estimated 1.9 billion physical qubits. That's the basic unit of quantum power. So what do we have today? Our best machines have a few hundred. So yeah, the gap is huge right now, but it makes the threat very real. The question isn't if the hardware will get there, but when.
And that brings us to the final crucial question. The elegant system that Satoshi designed was an amazing solution for the digital world of 2008. But as we step into this new quantum era, the race is on to develop new quantum-resistant cryptography. The challenge that once faced Bitcoin now faces our entire digital world. How do we build a new foundation of trust for a future we can't even fully imagine yet?